Hello, my name is João Pedro, and this is my final presentation on CFD, and it is on turbulent flow in automotives. And so the general purpose of this study was to investigate turbulent flow that is external and around a 2D car cross-section, and specifically varying the ride height and seeing how that affects the drag coefficient, the lift, and different flow phenomena. And so the geometry is a 2D cross-section of a car to reduce computational costs. And it was created in SolidWorks and then imported. And this is encased in a 2D wind tunnel. And both of these were kept constant to isolate the ground clearance effects. And I started with the KE model study for very quick conversions. And then I used the solution of this study in order to start the solution for the KW SST low Reynolds number, which has more improved near wall resolution and also more accurate vortices predictions. And so then a mesh study was conducted with the initial strategy of a very coarse triangular mesh in the regions that are far from the car, and then near the car, multiple levels of refinement. And the meshes were analyzed based on the drag force, the friction factor, and then the mass and momentum balance. And the final mesh that was chosen had around a 2 to 3% variation in the key quantities, which is very good. So the final mesh looked like this, and it had around 20,000 nodes. And so as you can see for velocity, there is a stagnation at the nose as well, which is the same as the pressure, high pressure, low velocity. And the streamlines are converging towards the nose. And then along the surfaces, there is high speed flow that accelerate over the roofline and also under the underbody. And again, this creates the Venturi effect, which can be more easily seen here. As you can see, there's actually two vortices, and the upper vortex is a little larger and expands more freely because of the slanted roof, and the lower vortex is actually compressed between the upper vortex and the ground, and this causes asymmetrical wake pressure, which is very bad for drag actually. And some 1D plots were also made for the velocity and pressure at different parts of the car to understand the flow better. But in the end, the lift and the drag were plotted against the height. And as you can see here for lift, there's definitely a correlation between ride height and the lift force. So this is theorized to be because of the underbody airflow and the ground effect. For low ride heights, it is surprisingly smaller downforce than some other ones. This very small clearance may limit the airflow acceleration, which may increase the underbody pressure. And because of that, there is weaker Venturi effects and then also less aerodynamic downforce. And then for intermediate heights around 25 centimeters, these were the most negative lift forces observed. And the flow decelerates very efficiently beneath the car. And then for higher ride heights, the downforce reduces again, which is expected because of the weakened ground forces and ground effect on the pressure differential. Because it is farther away, it's more of a symmetrical flow, and this induces less pressure-induced lift or downforce. And now for the drag graph, as you can see for low heights, there's actually a moderately high drag despite the very strong underbody acceleration. And this could be because of the very compressed lower vortex, as you saw earlier, which actually disrupts the wake recovery and then increases drag. For the intermediate height, again, at 25 centimeters, there is a peak drag force and coefficient observed. There's also possibly enhanced shear and very strong vortex formation at the back because of the vortices being more symmetrical, and also a delayed pressure recovery because of the low pressure zone caused by the more symmetrical flow vortices. And then for the higher ride heights, you can see the lowest drag levels in the whole parametric sweep. And this could be because of the underbody flow being weakened and thus leading to less vortex formations and less strong vortex formations, and just improved flow reattachment at the back. And then also the body is acting almost as an isolated bluff body and not as impacted by the ground, which reduces the turbulence in the underbody and thus reduces the drag. And yeah, that was pretty much it. Thank you very much for your time.